Welcome to the fascinating world of protein architecture. Today, we are going to explore how proteins, the fundamental building blocks of life, organize themselves into complex, functional machines. Just like a magnificent house is built from basic bricks, proteins are built from simple amino acids. We will discover how these basic units stack together to form intricate structures known as motifs, domains, and folds. Understanding this hierarchy is absolutely essential for anyone studying biochemistry or zoology, as it reveals the secret behind how life functions at a molecular level. Let us dive in and uncover the blueprints of biology. Now that we've introduced the topic, let us use a helpful analogy to understand protein architecture. Imagine you are building a complex house from scratch. You start with basic bricks, which represent our individual amino acids in a polypeptide chain. When you stack these bricks, you get walls and floors, which are like the secondary structures, known as alpha helices and beta sheets. But a house is not just random walls. You arrange them into specific archways or staircases, which we call motifs in biochemistry. Finally, you group these structures to form complete functional rooms, like a kitchen or bedroom, which perfectly represent protein domains. Building on our house analogy, let us look at the formal scientific definition of a motif. A motif, which is also known as a supersecondary structure, is a recognizable and recurring pattern formed by the spatial arrangement of two or more secondary structures. For example, a beta-alpha-beta loop is a very common motif where an alpha helix connects two parallel beta strands. However, it is important to note that a motif is usually not stable enough to maintain its shape if it is cut away from the rest of the protein. It needs the surrounding structure for support. Moving up the structural hierarchy from motifs, we arrive at domains and folds. A domain is a distinct, compact, and independently folding region of a polypeptide chain that usually carries out a specific biological function. Unlike a motif, if you were to sever a domain from the main protein, it would typically retain its three-dimensional structure and its function. This makes it a fundamental modular unit of protein evolution. Finally, a fold refers to the overall global three-dimensional topological arrangement of these motifs and secondary structures into a single, cohesive architectural design. Understanding these definitions is not just academic, it has profound real-world applications. Because domains are modular, nature acts like a molecular engineer, mixing and matching different domains during evolution to create entirely new proteins with novel functions. In the real world, pharmaceutical scientists design life-saving drugs by targeting specific functional domains of disease-causing proteins, such as the active site domain of a viral enzyme. If we did not understand how these domains fold and function, structure-based drug design would be completely impossible. Furthermore, recognizing specific motifs allows researchers to predict the function of a newly discovered protein simply by looking at its sequence. To make these concepts concrete, let us look at this visual representation of the protein hierarchy. On the far left, you can see a motif. Notice how it is just a simple recurring structural element, specifically a beta-alpha-beta loop, combining a few secondary structures. Moving to the center, we see a domain. Here, several motifs have folded together into a compact, independent unit that can perform a specific task. Finally, on the right, we see the complete fold of the protein. This global structure contains multiple distinct domains, shown in different colors, working together. This diagram perfectly illustrates how simple patterns build up into complex biological machines. Now that we can visualize the final folded state, we must ask how the protein gets there. Before a protein finds its stable fold, it exists as a flexible chain that could theoretically twist into countless different shapes. Cyrus Leventhal proposed a famous paradox, highlighting that if a protein tried every possible conformation randomly, it would take longer than the age of the universe to fold into its correct domain structure. This tells us that proteins absolutely do not fold by random chance. Instead, they must use specific folding pathways, guided by the rapid formation of local motifs. Let us look at the mathematics behind this paradox. To truly appreciate Leventhal's paradox, we can calculate the theoretical number of random conformations a polypeptide chain can adopt. This comes from a simple exponential relationship based on backbone flexibility. The formula is C equals 3 raised to the power of 2n. Conceptually, this represents every possible twist and turn the chain could make. C is the total number of possible theoretical conformations. The number 3 represents the approximate number of stable angles for each rotatable bond. The multiplier 2 is used because each amino acid has exactly 2 freely rotatable bonds in the main backbone, known as the phi and psi angles. Finally, n represents the total number of amino acids. As n increases, the number of conformations grows exponentially. Let us apply this formula to a concrete example to understand the sheer scale of the folding problem. Suppose we have a newly synthesized polypeptide chain that is exactly 50 amino acids long. We want to calculate the total number of possible conformations this chain could theoretically adopt if it searched at random. We know our n is 50. Because there are 2 flexible bonds per amino acid, we multiply 50 by 2, giving us 100 flexible bonds in this small domain. We substitute 50 into our exponent, giving us C equals 3 raised to the power of 2 times 50. Simplifying this, we get 3 to the power of 100. This shows the true mathematical magnitude of the protein's flexibility. Continuing from our previous step, we now need to evaluate this massive exponential expression, 3 to the power of 100. Even without a calculator, you can intuitively sense this will yield an astronomically large result. When we compute this, the final answer reveals that there are approximately 5.15 times 10 to the power of 47 possible conformations for this tiny 50 amino acid domain. To put this in perspective, if the protein tried 1 billion conformations per second, it would still take billions of years to fold. This physically proves that proteins rapidly form local motifs to guide folding, rather than searching randomly. Having proven that proteins do not fold randomly, we must ask what actually drives them to their final shape. To understand how these complex domains and folds form in nature, we must look at the thermodynamics of protein folding. Proteins do not just magically snap into their folded domain structures. They are driven by physical forces that constantly seek the lowest possible energy state. The stability of a folded protein domain is a delicate balance between the heat energy released when favorable bonds form and the loss of flexibility or disorder in the system. When temperatures increase significantly, the disorder term dominates, which is exactly why high heat causes proteins to unfold or denature. The thermodynamic balance we just discussed is mathematically represented by the Gibbs free energy equation. Conceptually, this fundamental principle tells us whether the folding process will happen spontaneously under cellular conditions. The formula is delta G equals delta H minus T times delta S. Let us break down every symbol. Delta G represents the change in Gibbs free energy. For a protein to fold spontaneously, this overall value must be negative. Delta H represents the change in enthalpy, accounting for the heat energy released when favorable chemical bonds, like hydrogen bonds, are formed. T represents the absolute temperature in Kelvin. Finally, delta S represents the change in entropy, which measures the degree of disorder. Folding restricts movement, so entropy usually decreases. Let us apply this thermodynamic equation to see what keeps a folded domain stable once it is formed. Imagine a specific protein domain folding at a physiological temperature of 298 Kelvin. During folding, the formation of hydrogen bonds releases heat, giving an enthalpy change of negative 250 kilojoules per mole. However, folding restricts the protein's movement, resulting in a loss of entropy, given as negative 0.6 kilojoules per mole Kelvin. We need to determine if this domain will fold spontaneously. We start by substituting our known values into the Gibbs free energy equation. We plug in negative 250 for delta H, 298 for T, and negative 0.6 for delta S. Continuing our calculation, we first multiply the absolute temperature by the change in entropy. This gives us negative 178.8 kilojoules per mole. This value represents the thermodynamic energy penalty the protein pays because it is becoming highly ordered and losing its flexible structure. Next, we subtract this negative value from our enthalpy, which mathematically turns into an addition. Negative 250 plus 178.8 gives us a final Gibbs free energy change of negative 71.2 kilojoules per mole. Because this final value is significantly negative, it physically means the favorable interactions were strong enough to overcome the penalty of losing flexibility, making the folding process entirely spontaneous and the domain highly stable. We have covered a lot of ground today, so let us summarize the most important ideas from this topic. First, we learned that protein architecture is built step by step. Motifs act as the basic structural patterns, which then assemble into domains, the independent functional workhorses of the protein. The overall arrangement of these domains gives the protein its unique fold. Second, through Levinthal's paradox, we saw that proteins do not fold by random chance, but are guided rapidly by local motifs. Finally, we proved that the entire process is driven and stabilized by thermodynamic forces, specifically the balance of enthalpy and entropy in the Gibbs free energy equation. You now have a solid fundamental understanding of how biomolecules achieve their life-sustaining shapes.